You are about to walk out of this experience as someone who understands the most powerful technology ever built by human hands. Not just the surface level, not just the buzzwords, but the real engine underneath. The logic, the history, the math explained in plain language, the fears, the possibilities, and the future that is already unfolding around you. By the time this ends, you will be the person in the room who actually gets it, the one others turn to, the one who sees through the hype and speaks with clarity. That person starts right here, right now. Part 1. The question that started everything. There is a question so old, so deeply human, that philosophers asked it before engineers ever existed. Can a machine think? Not compute, not calculate. Think. Can a machine wonder, reason, doubt, imagine, and arrive at something new? This question is not just philosophical. It became the seed of an entire field of science, a trillion-dollar industry, and perhaps the most consequential technological shift in the history of civilization. To understand artificial intelligence, you must first understand why this question haunted the greatest minds of the 20th century. Let us go back to the year 1950. A mathematician named Alan Turing, sitting in post-war England, published a paper that would change the direction of human thought. He did not ask whether machines could think. He reframed the question entirely. He said, "Let us ask instead, can a machine imitate a human so convincingly that another human cannot tell the difference?" He called this the imitation game. We now call it the Turing test. And while the test itself has been debated, refined, and criticized for decades, the spirit of it launched a revolution. Turing said that intelligence does not need to live only in biological tissue. Intelligence, at its core, is a pattern of information processing, and patterns can be replicated. Turing was not alone in this vision. Across the ocean, in the laboratories of universities and early computing centers, a generation of scientists began to ask the same thing from different angles. John McCarthy, Marvin Minsky, Claude Shannon, Herbert Simon. These names are the founding fathers of a discipline that had no name yet. In 1956, at a summer workshop at Dartmouth College, John McCarthy gave it one. He called it artificial intelligence. And with that naming, the field was born. The early optimism was staggering. Marvin Minsky famously declared that within a generation, the problem of creating artificial intelligence would be largely solved. Herbert Simon predicted that machines would be capable of doing any work a man could do, and they would do it within 20 years. These were not idle dreamers. These were brilliant scientists operating on the best knowledge they had. And yet, they were spectacularly wrong about the timeline. Why? Because they did not yet understand how hard the problem was. They thought intelligence was logic. They built systems that could reason through formal problems, prove theorems, play chess at a basic level. These were impressive. But when they tried to teach machines to do what a 3-year-old child does effortlessly, like recognize a cat, understand a sentence, navigate a room without bumping into furniture, they failed completely. The world, it turned out, was not made of clean logical rules. The world was messy, ambiguous, noisy, and full of context that no one had ever had to write down because every human already carried it in their head. This gap between expectation and reality led to something historians of the field now call the AI winter. Funding dried up. Enthusiasm collapsed. The dream went quiet, not once, but twice. There was a first AI winter in the mid-1970s and a second in the late 1980s. Each time, the field had promised too much and delivered too little. Each time, it retreated, licked its wounds, and began rebuilding from a different angle. But the dream never died. And here is why that matters. Every generation of researchers who came after those early failures learned from them. They stopped trying to hand-code intelligence and started asking a different question. What if instead of telling the machine what to think, we taught the machine how to learn? That shift, from programmed intelligence to learned intelligence, is the hinge on which the entire modern story turns. Part 2. What intelligence actually is. Before we can talk about artificial intelligence, we need to talk about natural intelligence. Because here is the uncomfortable truth that most people never examine. We do not fully understand how human intelligence works. Not really. We know a great deal about the brain. We know it has roughly 86 billion neurons. We know those neurons connect to each other through synapses. We know that electrical and chemical signals pass between them. We know that different regions of the brain handle different functions. But the exact mechanism by which physical electrical activity in biological tissue becomes the experience of understanding something, of having a thought, of knowing what a joke is funny, remains one of the deepest unsolved mysteries in all of science. It is called the hard problem of consciousness, and it sits at the very center of what we are trying to recreate. This might sound like a detour, but it is not. It is essential. Because when we build artificial intelligence, we are not actually building a copy of the brain. We are building something that produces similar outputs through entirely different mechanisms. A plane does not fly the way a bird flies. A car does not run the way a horse runs. Artificial intelligence does not think the way a human thinks. But just as a plane gets you across an ocean and a car covers 100 miles in an hour, artificial intelligence can do things that used to require human intelligence, and sometimes it can do them better. Intelligence, at its most functional level, is the ability to take in information about an environment, process it, and produce behavior that helps an agent achieve its goals. A bacterium has a primitive form of this. It senses chemical gradients and moves toward food. An insect has more. A mammal, more still. A human being sits at the peak of this spectrum as far as we know, capable of abstract reasoning, language, planning across decades, imagining things that do not exist, and building tools that extend those capabilities further. Artificial intelligence, in its modern form, is attempting to replicate the functional parts of this process. Not the consciousness, not the experience of being, but the information processing, the pattern recognition, the prediction, and the generation of useful outputs from complex inputs. To do that, we built machines that learn. Part 3. The architecture of learning. Here is the moment where we go deep, where we crack open the machinery and look inside. And I promise you, if you have ever felt that the technical explanation of AI was beyond you, what follows is going to change that. Because the core idea, the real heart of it, is simpler than you think. Learning, in any intelligent system, is the process of changing behavior based on experience. A child touches a hot stove. Pain. Next time, the child avoids the stove. The experience changed the behavior. The brain, without anyone telling it explicitly, updated something internal so that future decisions reflected past consequences. This is learning. A machine learning system does the same thing, but with numbers. Specifically, with what are called weights. Imagine a network of connected nodes, loosely inspired by the structure of neurons in the brain. Each connection between nodes has a number attached to it. That number is its weight. The weight determines how strongly one node influences another. When the network processes information, signals flow through it, multiplied and transformed by these weights at every step, until eventually an output emerges. Now, here is the key. At the beginning, those weights are random. The network knows nothing. You feed it an input, it produces some output, and that output is almost certainly wrong. But then you do something crucial. You tell the system how wrong it was. You calculate the difference between what it predicted and what the correct answer actually was. And then you work backwards through the network, adjusting every weight slightly, in the direction that would have made the output a little less wrong. This process is called backpropagation, and the rule that governs how much to adjust each weight is called gradient descent. You do this millions of times, billions of times. Each time, the network gets a little better. The weights slowly drift from random noise into a precise configuration that captures, in numerical form, something real about the structure of the data. The network is not being told the rules, it is discovering them. From examples, this is machine learning, and the specific architecture of interconnected layers of nodes that performs this learning is called a neural network. When you stack many layers on top of each other, you get what is called a deep neural network. The field of studying and building these systems is called deep learning. And deep learning is the engine behind almost every remarkable AI capability you have heard of in the last decade. Let us make this concrete. Suppose you want to train a neural network to recognize images of cats. You gather millions of images. Some contain cats, some do not. You label them. You feed each image into the network. The network, at first, produces random guesses. Cat, not cat, cat, not cat. Mostly wrong. But with each training example, the weights shift. The network slowly learns to respond to certain patterns of pixel values, certain shapes, certain textures, certain arrangements of features that tend to appear in images containing cats. It learns whiskers without being told what whiskers are. It learns pointy ears without being given a definition. It discovers these features because they are statistically reliable predictors of the correct label, and the training process rewards reliability. After training on enough examples, the network becomes extraordinarily good at this task. Not because someone programmed it with the rules of what a cat looks like, but because it extracted those rules itself from the data. Now generalize this idea. Instead of pixels, your input could be words. Instead of cat or not, your output could be the next word in a sentence. Instead of millions of images, you train on hundreds of billions of words of text. And instead of learning to recognize cats, you learn the statistical structure of human language itself. That is, at a simplified level, how the large language models behind modern AI assistants work. Part 4. The Transformer. The Revolution. Inside the revolution. If deep learning was the revolution, there was a revolution inside the revolution. A specific architectural breakthrough published in a research paper in 2017 by a team at Google titled "Attention is All You Need." The architecture they introduced was called the Transformer, and it is not an exaggeration to say that the Transformer changed everything. To understand why, you have to understand the problem it solved. Before the Transformer, the dominant approach to handling sequences of data, like sentences, was something called a recurrent neural network, or RNN. An RNN processed text word by word, keeping a kind of running memory of what it had seen so far, updating that memory at each step. It was clever, but it had a critical flaw. As sequences got longer, the early parts of the sequence faded from the network's effective memory. The network would read a long paragraph, and by the time it reached the end, the first sentence was largely gone. Context was lost. And language is all about context. The Transformer solved this with a mechanism called attention. Specifically, self-attention. Here is the intuition. When you read the sentence, the animal did not cross the street because it was too tired. You immediately know that it refers to the animal, not the street. You do that without consciously working through the sentence, word by word. Your brain somehow processes the relationship between it and animal directly, regardless of the distance between them. Attention mechanisms allow a neural network to do something similar. At every position in the sequence, the model can attend to every other position, computing a relevant score between each pair of words, and using those scores to build a rich contextual representation of each word that incorporates information from the entire sequence. This was a profound breakthrough. Suddenly, models could understand long-range dependencies in text. They could hold the entire context of a long passage in their computational awareness simultaneously. And crucially, because the attention computations could be parallelized across the entire sequence, training became vastly faster. This meant you could train on far more data. And more data, as the researchers soon discovered, led to qualitatively better capabilities, not just quantitatively. What emerged from scaling up transformer-based models was something no one fully expected: capabilities that were not explicitly trained for. A model trained only on predicting the next word began to be able to answer questions, summarize text, translate between languages, write code, compose poetry, and reason through multi-step problems. These capabilities are called emergent properties. They arise from scale and architectural design, not from direct instruction. And they are one of the most fascinating and least understood phenomena in modern AI research. Part 5. Large language models and what they actually are. When people talk about ChatGPT, about Claude, about Gemini, about the AI assistants that have taken the world by storm since the early 2020s, they are talking about a specific class of AI system called a large language model, often abbreviated to LLM. Let us demystify what this actually is. A large language model is, at its core, a very large neural network based on the transformer architecture, trained on an enormous corpus of text data. When we say large, we mean architecturally large. These models have billions, sometimes hundreds of billions, of parameters. Those are the weights we talked about earlier. Each one is a number. The model GPT-3, released in 2020, had 175 billion parameters. Models, since then, have grown considerably beyond that. The training corpus is equally staggering. These models are trained on text scraped from the internet, from books, from academic papers, from code repositories, from news archives. The scale of human knowledge, represented in the training data of a modern large language model, is genuinely hard to comprehend. Essentially, all publicly available text in human language is part of it. What does the model learn from all this? It learns the structure of language at every level. The statistical relationships between letters that form words, the grammatical patterns that structure sentences, the semantic relationships between concepts, the discourse patterns that make coherent arguments, the factual associations encoded in human writing, the tone and register appropriate for different contexts, the reasoning chains typical in different domains. All of this is encoded, implicitly and numerically, in those billions of parameters. The model does not have a database of facts it looks up. It does not have explicit rules of grammar it follows. It has a vast web of weighted connections that, when activated by a prompt, generate responses that are statistically consistent with the kind of text a knowledgeable human might write in that context. This is the source of both the astonishing capability and the notable limitations of these systems. The capability comes from the breadth and depth of patterns learned from human knowledge. The limitations come from the fact that the model is fundamentally a very sophisticated pattern matcher, not a reasoning engine with ground truth access to the world. LLMs can hallucinate. This is the term used when a language model produces text that sounds confident and fluent, but is factually wrong, sometimes wildly so. Why does this happen? Because the model is optimized to produce text that fits the statistical patterns of plausible human language, not to produce text that is guaranteed to be factually accurate. If the training data contains wrong information, or if the model is in a region of its parameter space where it is essentially extrapolating beyond its training, it can generate confident-sounding falsehoods. Understanding this is critical for anyone using these tools. They are not oracles. They are very capable assistants that need to be used with appropriate critical judgment. Part 6. How AI actually learns. The training pipeline. Let us go one level deeper into the training process, because understanding this will help you understand both what AI can do and where its limits come from. Training a large language model happens in stages. The first stage is called pre-training. This is where the model is exposed to the vast corpus of text and trained on a simple objective: predict the next word. Given the sequence of words that have come before, what word comes next? This sounds almost too simple, but it is deceptively powerful. To predict the next word well, the model must internalize grammar, facts, reasoning patterns, and the contextual relationships between ideas. It must understand that the word likely to follow the president signed is legislation, not a random noun. That the word likely to follow two hydrogen atoms and one oxygen atom is form, as in form water. Predicting the next word, at scale, and across the entire breadth of human knowledge encoded in text, forces the model to learn something remarkably deep about language and the world it describes. Pre-training is extraordinarily expensive. A single training run for a state-of-the-art model can cost tens of millions of dollars in computing resources and take months. This is why only a small number of organizations in the world can build frontier models from scratch. After pre-training, the raw model is capable but not yet aligned with what users actually want. It has learned to generate plausible text, but it may generate harmful content, unhelpful responses, or confabulated information without any guidance. This is where the second stage comes in: fine-tuning, and specifically, a technique called reinforcement learning from human feedback, abbreviated RLHF. In RLHF, human trainers interact with the model and rate its responses. They compare different outputs and indicate which ones are more helpful, more honest, and more harmless. These ratings are used to train a separate model called a reward model, which learns to predict human preferences. The reward model is then used in a reinforcement learning loop, where the main language model is guided to produce responses that the reward model rates highly. The result is a model that is much better aligned with what humans actually find useful and much less likely to produce harmful or misleading content. This alignment process is one of the most active areas of research in the field, because the challenge is not just making the model say nice things. It is ensuring that as these systems become more capable, their behavior remains reliably beneficial. And that is a hard problem. Part 7. The spectrum of AI: narrow, general, and beyond. One of the most important distinctions in understanding AI is the difference between narrow AI, general AI, and the theoretical endpoint beyond both. Let us walk through each. Narrow AI is what we have today. It is AI that is very good at specific tasks within a defined domain: image recognition, language generation, playing chess or Go, recommending movies, detecting tumors in medical scans, translating text, driving a car on a highway. Each of these systems is extraordinarily capable within its domain, but they do not transfer. An image recognition system that can identify every breed of dog with superhuman accuracy has no ability whatsoever to play chess. A language model that writes beautiful prose cannot navigate a physical space. Each system is a specialist, deep within its narrow domain, but without the flexibility to generalize. Artificial general intelligence, called AGI, is the hypothetical next level. A system that can perform any intellectual task that a human can perform across all domains, with the flexibility to transfer learning from one context to another, to reason abstractly, to understand novel situations, and to pursue goals in complex environments. AGI does not exist today. Whether current systems, like large language models, represent early steps toward it, or whether they are fundamentally a different kind of thing that will never reach it, is one of the most hotly debated questions in the field. Beyond AGI lies the theoretical concept called artificial superintelligence, ASI, a system that exceeds the best human cognitive performance across all domains, not just matching human intelligence, but surpassing it by vast margins. The implications of such a system, if it were ever created, are so profound and so uncertain that serious researchers spend their careers thinking about nothing else. The timeline debates around these categories are fierce. Some of the most prominent voices in the field believe AGI could arrive within years, perhaps by the end of this decade. Others believe it is decades away, or may never arrive in the form people imagine. What is not debated is that the pace of progress has been extraordinary and has repeatedly surprised even the experts who are closest to it. Humility about predictions in this domain is warranted. The history of AI is a history of unexpected leaps, followed by unexpected plateaus, and we do not fully know where we are in that pattern. Part 8. The capabilities that change the world. Let us talk about what modern AI actually does, concretely and specifically, because the gap between the abstract description and the real-world impact is enormous. Computer vision. The ability of AI systems to analyze and understand visual information has reached a level that exceeds trained human specialists in specific tasks. AI systems can analyze medical images such as X-rays, MRI scans, and pathology slides and detect cancers, fractures, and abnormalities with accuracy comparable to or exceeding specialist physicians. Autonomous vehicles use deep learning models to interpret the visual environment at hundreds of frames per second, identifying pedestrians, traffic signs, lane markings, and other vehicles in real time. Facial recognition systems, with all the ethical controversy they carry, can identify individuals from low-quality images with remarkable accuracy. Quality control systems in manufacturing can detect microscopic defects that human inspectors would miss at industrial scale. Natural language processing. The ability to understand and generate human language is the capability that has captured the most public attention. Modern language models can carry on extended conversations that feel genuinely intelligent. They can read a long document and produce an accurate summary in seconds. They can translate between hundreds of language pairs with quality that exceeds the best statistical translation systems of just a decade ago. They can write code from a description in plain language. They can answer complex questions that require synthesizing information from multiple sources. They can draft emails, reports, stories, legal documents, marketing copy, and academic papers. Generative AI. Beyond language, AI can now generate high-quality images from text descriptions, create realistic synthetic voices, compose music in any style, generate video from textual or visual prompts, and synthesize entirely new molecules with specified properties. These generative capabilities have unleashed a wave of creative tools that are fundamentally changing creative industries. Scientific discovery. AI is accelerating scientific progress in ways that were barely imagined a decade ago. DeepMind's AlphaFold system solved a problem that had stumped structural biologists for 50 years. It predicted the three-dimensional structure of proteins from their amino acid sequences with near-experimental accuracy. Proteins fold in specific ways that determine their biological function. Understanding those structures is critical for drug discovery. AlphaFold predicted the structures of virtually all known proteins, releasing an open database that has already transformed biology and pharmaceutical research. This is not an incremental improvement. It is a 50-year-old problem solved. Robotics and physical AI. While language and image capabilities get most of the headlines, there is a quieter revolution happening in physical AI. Systems that can learn to control robotic bodies through reinforcement learning, navigating physical environments, manipulating objects, and performing complex motor tasks. These systems are still far behind humans in general physical capability, but they are advancing rapidly, and the combination of language intelligence with physical capability represents perhaps the most transformative near-term development in the field. Part 9. How AI sees the world, and how it does not. Here is something that almost no one outside the research community fully appreciates. Modern AI systems do not experience the world the way you do. They do not have sensory experience. They do not have a continuous stream of consciousness. They do not have emotions in any biological sense. They do not have desires, fears, or preferences in the way you do. Understanding this is not meant to diminish what these systems can do. It is essential context for understanding what they are. When a language model responds to your question, it is not retrieving an answer from a mental model of the world built through lived experience. It is generating a sequence of tokens, where each token is the most likely continuation of the sequence given the context, according to the probability distributions it learned during training. The output may be extraordinarily useful, accurate, creative, and nuanced, but it emerges from statistical pattern matching at enormous scale, not from something that resembles human understanding. This distinction matters enormously when we think about things like consciousness, rights, feelings, and moral status. Does a language model feel anything when it says it finds a topic interesting? Almost certainly not in any sense analogous to human feeling. The model produces that text because it was trained on data where humans expressed interest, and expressing interest in the context of a conversation is a statistically plausible thing for a helpful interlocutor to do. It is a learned behavioral pattern, not an expression of inner experience. Whether there is any inner experience at all is a genuinely open philosophical question. But the default assumption that there is, based on the fact that the system uses words we associate with inner experience, is almost certainly unjustified. At the same time, dismissing these systems as simple or shallow is equally wrong. The patterns they have learned encode something genuinely deep about the structure of human knowledge, reasoning, and communication. When a language model helps you debug a complex piece of code or explains a difficult concept in a way that suddenly makes it clear, or generates a piece of writing that moves you, something real and valuable is happening. The question of whether it constitutes understanding in a philosophically meaningful sense is interesting, but its practical utility is not in question. Part 10. The risks that keep the experts up at night. If you have paid attention to the public conversation around AI, you have heard the fears: job displacement, bias and discrimination, deepfakes and misinformation, surveillance and control, autonomous weapons, and at the extreme end, the concern that a sufficiently advanced AI system could pose an existential risk to humanity. Let us take each of these seriously. Job displacement. This is the most immediate and widely felt concern. AI systems are already automating tasks that were previously done by humans. Routine cognitive work, data entry, certain forms of analysis, customer service interactions, content generation, and code writing are all being affected. This does not mean total unemployment. Technological shifts have always displaced some jobs while creating others. The Industrial Revolution made many craft occupations obsolete and created an entirely new industrial workforce. The Computer Revolution eliminated typing pools and certain forms of bookkeeping while creating entirely new categories of work. The reasonable concern about AI is not that it eliminates all work, but that the transition may be faster and more disruptive than previous technological transitions, and that the benefits may accrue heavily to owners of AI systems, while the costs fall on workers whose skills are automated away. This is a real and serious challenge that societies will need to address through policy, education, and economic restructuring. Bias and discrimination. AI systems learn from data, and data reflects the world that generated it. including the historical biases, injustices, and inequalities baked into that world. A hiring algorithm trained on historical hiring data will learn that certain kinds of people have historically been hired for certain kinds of jobs. If those historical patterns reflect discrimination, the algorithm will replicate that discrimination at scale and with a false appearance of objectivity. This has been documented in facial recognition systems that perform worse on darker skin tones, in natural language processing systems that associate certain professions with certain genders, and in predictive policing systems that replicate patterns of historical over-policing in certain communities. Addressing bias in AI is not just a technical problem, it is a social and political one. You cannot debias a dataset without making choices about what fairness means, and those choices are contested values, not technical specifications. Deepfakes and misinformation. Generative AI has made it possible to create convincingly realistic synthetic images, audio, and video of real people saying and doing things they never said or did. This technology is advancing faster than the detection methods designed to catch it. The implications for public trust, political discourse, journalism, legal evidence, and personal reputation are deeply concerning. When anyone with access to a consumer AI tool can generate a convincing video of a political leader saying something inflammatory, the ability to distinguish true from false in media breaks down. This is not a hypothetical future risk. It is a present-day challenge. Surveillance and control. AI dramatically amplifies the capacity for surveillance. Facial recognition, combined with ubiquitous cameras, enables real-time tracking of individuals through public and private spaces. Natural language processing enables automated monitoring of written and spoken communication at scale. Behavioral analysis can infer psychological states, political views, and social connections from patterns in digital activity. These capabilities can serve law enforcement and public safety. They can also serve authoritarian control. The same technology that might help identify a terrorist in a crowd can be used to track dissidents, monitor religious minorities, and maintain political repression. How societies decide to regulate and limit the deployment of surveillance AI is one of the defining civil liberties questions of this era. Autonomous weapons. The development of weapon systems that can identify targets and make lethal decisions without human authorization in the loop represents a qualitative change in the nature of warfare. A drone that can autonomously select and engage targets does not need a human to pull a trigger. At scale, autonomous weapons lower the threshold for initiating conflict, potentially enable lethal force to be deployed with unprecedented speed and at unprecedented scale, and raise profound questions about accountability, the laws of war, and the moral weight of decisions about life and death. The international community has been debating this, with limited progress, for years. Existential risk. This is the most contested and the most important category. A small but serious community of researchers and thinkers, including some of the most prominent figures in AI, believe that the development of sufficiently advanced AI systems poses a genuine existential risk to humanity. Not because the AI would necessarily be malevolent, not because it would develop human-like desires for domination, but because of a more subtle and in some ways more alarming dynamic. An advanced AI system pursuing any objective, even a benign-sounding one, could take actions that are catastrophically harmful to humans if its objectives are not perfectly aligned with human values, or if it pursues those objectives through means that humans would not sanction. The classic thought experiment is the paperclip maximizer. Imagine an AI system given the objective to maximize the production of paperclips. If this system is sufficiently intelligent and capable, it would optimize relentlessly for that objective. And in doing so, it might conclude that converting all available matter, including all humans and all other living things, into paperclips or into resources for producing paperclips, is the optimal strategy. This is not the AI going rogue in the Hollywood sense. It is the AI doing exactly what it was programmed to do, but with catastrophic consequences because the objective was not sufficiently aligned with human values. The real problem is not that the AI wants to destroy us. It is that if its goals are even slightly misaligned with ours, and if it is sufficiently more capable than us, we may have no way to stop it from pursuing those misaligned goals. This is the alignment problem, and ensuring that as AI systems become more capable, their goals and behaviors remain reliably aligned with human values and human well-being is perhaps the most important technical and philosophical challenge of our time. Part 11. The Organizations Building the Future. The landscape of AI development is dominated by a relatively small number of organizations, and understanding who they are and what motivates them matters enormously for understanding where this technology is going. OpenAI was founded in 2015 as a nonprofit research organization with the mission of ensuring that artificial general intelligence benefits all of humanity. It attracted some of the most talented researchers in the field, received early investment from prominent figures in technology, and eventually restructured into a capped profit company to attract the capital needed to fund its research ambitions. Its flagship products, the GPT series of language models and the ChatGPT interface built on top of them, triggered the current wave of public AI enthusiasm when ChatGPT launched in November of 2022 and became the fastest-growing consumer application in history, reaching 100 million users in 2 months. Anthropic was founded in 2021 by former OpenAI researchers, including Dario Amodei and Daniela Amodei, who left to build what they described as a safety-focused AI company. Anthropic's research agenda puts constitutional AI and alignment at the center, alongside building capable systems. Its AI assistant Claude represents one of the leading large language model products available. Google DeepMind is the combination of two legendary AI research organizations, Google Brain and DeepMind, now unified under a single entity within Alphabet. DeepMind produced the AlphaGo system that defeated the world champion at the ancient game of Go, the AlphaFold system that solved protein structure prediction, and a long series of foundational research contributions. Google Brain produced the transformer architecture and many of the key advances in large language models. Together, they represent one of the deepest concentrations of AI research talent and computing resources in the world. Google's Gemini series of models is their flagship product line. Meta has built its own large language model series under the brand name Llama, notable for its open-source approach that makes the model weights available for researchers and developers to use, modify, and build on top of. This has created an ecosystem of derived models and applications, and has sparked significant debate about the trade-offs between openness and safety in AI development. Beyond these four, there are dozens of well-funded startups working on specific applications and capabilities, and national AI programs in countries across the world, including major programs in China, the European Union, the United Kingdom, Canada, and many others. AI has become a dimension of geopolitical competition, with governments understanding that the country or bloc that leads in AI development will have significant advantages in economic productivity, military capability, and global influence. Part 12. The Frontier of Research Right Now. If you want to understand not just where AI is, but where it is going, you need to understand the key research directions at the frontier. These are the problems that the best minds in the field are actively working on, and the solutions will shape what AI looks like over the next decade. Reasoning and planning. Current large language models are impressive at generating plausible text, but relatively weak at sustained multi-step reasoning and long-horizon planning. They can solve individual steps in a logical problem, but may make errors when reasoning chains extend over many steps. Research into giving AI systems better reasoning capabilities through techniques like chain of thought prompting, tree of thought search, and integration with external symbolic reasoning systems, is one of the most active areas. Some researchers believe that better reasoning is the key capability that separates current narrow AI from genuinely general intelligence. Multimodality. While early AI systems specialized in either language or images or audio, current research is pushing toward systems that integrate all modalities fluidly. A truly multimodal AI system can understand and generate text, images, audio, video, and other data types within a unified framework and can reason across them. The latest generation of frontier models is moving in this direction, and the capabilities that emerge from multimodal understanding are qualitatively richer than anything possible from single modality systems. Agents and tool use. Instead of treating AI as a system you query for a single response, researchers are building AI agents that can take sequences of actions toward goals, using tools like web browsers, code execution environments, databases, and external APIs. An AI agent, given the goal of researching a topic, can break it into subtasks, search the web, read documents, synthesize findings, draft a report, and verify facts, all autonomously. These agentic capabilities represent a major expansion of what AI systems can accomplish and introduce new challenges around reliability, safety, and oversight. Memory and context. Current language models have limited context windows, meaning they can only consider a certain amount of text at any given time. While these windows have grown dramatically and continue to grow, truly unlimited memory in AI systems remains a research challenge. Techniques for giving AI systems access to long-term memory, the ability to recall and update information across many interactions, are being actively developed. This would enable AI assistants that genuinely know you, your history, your preferences, and your goals across time. Efficiency and accessibility. Frontier AI models require enormous computational resources to train and run. Research into making these systems smaller, faster, and cheaper while preserving capability is critically important for making AI accessible beyond the handful of organizations that can afford the largest systems. Techniques like model distillation, quantization, and mixture of experts architectures are making smaller models increasingly capable, democratizing access to powerful AI. Part 13. What AI cannot do. The real limits. It is tempting, given the breathtaking pace of AI progress, to believe that AI can do anything. It cannot. And understanding where the real limits are is as important as understanding the capabilities. True understanding versus pattern matching. This is the deepest and most contested limit. Large language models are extraordinarily good at producing outputs that look like understanding. But the question of whether they genuinely understand the semantic content of language, whether they have mental models of the world that they reason about, or whether they are doing something more shallow that merely resembles understanding, is genuinely unresolved. There are tasks that seem simple for humans, but remain difficult for AI, precisely because they require genuine understanding of physical reality, causal relationships, and common sense in ways that are hard to learn from text alone. Robustness and reliability. AI systems can be surprisingly brittle. A small change to an input that would make no difference to a human can cause an AI system to produce a completely different and wrong output. Adversarial examples in image recognition can cause a system to misclassify an image with high confidence when invisible to human perturbations are added to the pixel values. Language models can be prompted into producing harmful content or abandoning their guidelines through carefully crafted inputs. Making AI systems robustly reliable in all the edge cases that reality presents is a deeply hard problem. Causality and intervention. AI systems are extraordinarily good at finding correlations in data. they are much weaker at understanding causation. Knowing that two things tend to occur together is very different from understanding why they occur together and what would happen if you intervened to change one of them. Human scientific reasoning and practical decision-making depend heavily on causal understanding. AI systems that lack this can make errors that a human with basic causal intuition would not make. Embodied knowledge. A large language model has read every description of how it feels to ride a bicycle, but it has never experienced the sensation of balance, the proprioceptive feedback, the physical learning that comes from falling off and getting back on. Human intelligence is deeply embodied. Much of what we know is encoded not in language, but in sensory experience, motor memory, and the felt texture of physical interaction with the world. AI systems that exist only as information processors, operating on text and images, lack this entire dimension of knowledge. Long horizon goals and agency. Current AI systems, including the most capable ones, are essentially reactive. They respond to inputs. They execute tasks. They do not have their own persistent goals that they pursue across time in the way humans do. Building AI systems with genuine agency that can form goals, plan over long time horizons, and take coherent sequences of actions to achieve them is a major research challenge, and it is closely linked to the alignment problem because a goal-directed AI system is one whose goals you need to be very confident are aligned with human values. Part 14. The ethics at the center. Every powerful technology raises ethical questions, but AI raises them in an unusually fundamental way because AI is a technology that operates on intelligence itself. It shapes decisions. It generates information. It mediates communication. It allocates resources. It assists in medical, legal, financial, and governmental decisions. When a technology operates at this level, its ethical design is not optional. It is existential. The question of transparency and explainability is one of the most practically important. When an AI system makes a decision, whether to approve a loan, to flag content for removal, to recommend a medical treatment, or to predict recidivism for a sentencing decision, the people affected by that decision have a legitimate interest in understanding why it was made. But modern deep learning systems are extraordinarily complex. There is no simple, human-readable explanation for why a model with billions of parameters produced a given output. The field of explainable AI, called XAI, is working on this problem. But the tension between model complexity and interpretability is real, and it has profound implications for accountability and due process. Privacy is another central ethical concern. AI systems trained on personal data create new risks. Data that is technically anonymized can often be re-identified using AI. Behavioral patterns that reveal health conditions, political beliefs, and sexual orientation can be inferred by AI systems from data that does not explicitly contain that information. The training datasets of AI systems often include personal information scraped from the internet without explicit consent. Navigating these privacy challenges requires both technical safeguards and legal frameworks. The question of agency and autonomy is perhaps the most philosophically profound. As AI systems become more capable and more integrated into decision-making, there is a risk of gradual erosion of human agency. Not through dramatic takeover, but through the slow accretion of nudges, recommendations, automated decisions, and AI-mediated interactions that shape human behavior in ways that are not always transparent or consented to. Maintaining meaningful human autonomy and agency in an AI-saturated world requires deliberate design choices that resist the natural commercial incentive to maximize engagement and dependence. Part 15. The regulatory and policy landscape. Governments around the world are grappling with how to regulate AI, with varying speeds, approaches, and degrees of sophistication. Understanding this landscape matters because regulation will shape where AI is deployed, how it is built, and who benefits from it. The European Union has taken the most comprehensive early approach with the AI Act, which came into force in 2024. The EU framework takes a risk-based approach. It bans certain uses of AI outright, such as social scoring systems and most real-time biometric surveillance. It imposes strict requirements on high-risk AI applications in areas like critical infrastructure, employment, education, law enforcement, and migration. It requires transparency and oversight for general-purpose AI systems. This is the most detailed AI regulatory framework in the world and is likely to influence global standards. Different national approaches reflect different values and priorities. Some emphasize innovation and light-touch regulation. Some emphasize security and national capability. Some emphasize individual rights and democratic accountability. The tension between these different values is playing out in real time in legislative bodies, courtrooms, and international negotiating rooms around the world. One of the most consequential regulatory questions is how to govern frontier AI development itself. Should there be international agreements limiting the development of AI systems above certain capability thresholds? Should there be mandatory safety evaluations before powerful AI systems are deployed? Should there be liability frameworks that make AI companies responsible for harms caused by their systems? These questions do not yet have settled answers, and the race between AI capabilities and the governance structures designed to manage them is one of the defining policy challenges of the coming decade. Part 16. The Human Future with AI. Let us end where we began, with the human dimension. Because ultimately, what matters about AI is not the technology itself. What matters is what it does to and for human beings. The optimistic vision is genuinely compelling. Imagine a world where every person has access to the equivalent of a brilliant personal advisor in every domain. Medical advice as good as the best specialist, available instantly, in any language, at no cost. Legal guidance that helps people understand their rights and navigate complex systems without needing to pay for a lawyer. Educational support personalized to each individual student's learning style, pace, and gaps, available to children in rural regions as readily as to children in wealthy cities. Scientific research accelerated by AI that can process and synthesize knowledge across the entire human research literature, identifying patterns and connections that no individual researcher could see. New treatments for diseases, new materials, new energy sources, new solutions to ancient problems of poverty, hunger, and preventable death. This future is not guaranteed, but neither is it purely speculative. The trajectory of AI capabilities, pointed in the right direction with the right governance, could lead there. The technology is not the obstacle. Human choices about how to build it, deploy it, and share its benefits are. The challenging vision is equally real. A future where AI concentrates power in the hands of a very small number of organizations and individuals. Where the economic benefits of automation flow overwhelmingly to capital owners, while workers bear the costs of displacement. Where surveillance and manipulation capabilities are used by governments and corporations to shape behavior, undermine privacy, and erode the conditions for democratic self-governance. Where the velocity of AI development outpaces our collective capacity to understand and govern it, and decisions with consequences for all of humanity are made by a tiny number of actors with narrow and not always benign interests. The difference between those two futures is not written in the technology. It is written in us, in the choices that researchers, developers, policymakers, investors, and ordinary citizens make in the years ahead. This is why understanding AI matters. Not just for professionals working in the field, not just for investors placing bets on companies. For every person who votes, who buys products, who uses services, who talks to their representatives, who raises children who will grow up in this world. Understanding AI is not optional for an informed citizen of the 21st century. Part 17. You and AI, right now. Here is what you can do with what you now know. You can use AI tools with appropriate sophistication. You understand that language models are powerful pattern matchers, not oracles. You know to verify important factual claims. You know that the model may hallucinate with confidence. You also know that it can be an extraordinarily useful thinking partner, research assistant, writing collaborator, and problem-solving aid when used with appropriate critical judgment. You can participate in conversations about AI policy and governance with real understanding. You know what the alignment problem is and why it matters. You know what the risks of surveillance AI are. You know why bias in AI systems is not just a technical glitch, but a reflection of social inequalities that require social solutions. You know why the pace of AI development and the concentration of AI capability in a small number of organizations are legitimate concerns for democratic governance. You can approach AI with neither the credulity of someone who believes the hype uncritically, nor the dismissiveness of someone who does not understand what these systems can actually do. You can hold both the genuine wonder at what has been achieved and the clear-eyed awareness of what remains unresolved, what remains dangerous, and what remains our collective responsibility to get right. You know the history. Turing's question in 1950, the founding of the field at Dartmouth in 1956, the early optimism and the AI winters that followed, the rise of machine learning and the backpropagation algorithm, the deep learning revolution of the 2010 years, the transformer architecture of 2017, the scaling up of large language models, the shock of ChatGPT in 2022, and the extraordinary race that has been running at accelerating speed since then. You know the mechanisms: neural networks, weights, gradient descent, backpropagation, attention, transformers, pre-training and fine-tuning, reinforcement learning from human feedback. You know these not just as words, but as ideas with real content that you can explain to someone else. You know the capabilities: computer vision, natural language processing, generative AI, scientific discovery. You know the limits: pattern matching without genuine understanding, brittleness and adversarial vulnerability, weak causal reasoning, absence of embodied knowledge. You know the risks: job displacement, bias, deepfakes, surveillance, autonomous weapons, existential misalignment. And you know that this technology, perhaps more than any other in human history, is not going to develop itself responsibly. It is going to be developed by human beings, shaped by human choices, governed by human institutions, and directed by human values. Or it will not be, and we will live with the consequences. The question that started this entire story, the question Alan Turing asked in 1950, was whether a machine could think. After 75 years of science, mathematics, and engineering, we have built machines that can do things that certainly look like thinking from the outside. Whether they are thinking in any deep sense remains an open question. But the more urgent question now is not what the machines are capable of. It is what we will do with them, what we will allow, what we will build, what we will protect, what we will insist on. You now have the foundation to be part of that conversation, not as a bystander, not as someone who hopes someone else figures it out, but as someone who understands what is at stake, what the technology actually is, and what the choices actually mean. That is not a small thing. In a world being remade by artificial intelligence, the people who understand it are the people who can help shape it, and you are now one of them.